Good day, students. In this clip, we're going to be going over the art of finding the definite integral. We're going to be reviewing most of the concepts we covered in chapter 5. So let's get started by taking a look at number 1. We're to use the given velocity time chart to estimate the distance covered by a traveling object in the first 24 seconds using left endpoint rectangular approximation. All right, so what we're looking for here is the distance covered in the first 5 seconds. So that distance is going to basically be given by the definite integral expression, the integral from 0 to 24, actually the first 24 seconds, of the velocity function dt. Okay, this expression gives you the exact distance covered from in the first 24 seconds. But we don't have a function here, so and we just have a chart. So the best we can do is approximate what the total distance covered is. So to calculate that, we're going to be finding an approximate value using the left-hand rectangular approximation. Okay. All right. So if you notice here, it looks like our intervals are not equal, so we cannot use the other formula for equal subintervals. Let me show you what that formula is. If you have equal subintervals, you can use the formula. LRAM is basically W times f of x1 plus f of x2 plus the pattern goes on, f of xn minus 1. Okay, so this is when you have equal subintervals. In this case, our width or subintervals are not equal, so we cannot use this formula here. All right, so in order to determine what our various widths are, we're going to actually have to sketch the interval and compute what the width is. In this formula with equal subintervals, you can simply compute W by finding the length of the interval divided by the number of equal subintervals that you're going to use. Okay? Now let's draw a number line illustrating the range of our time interval. We're going from 0 all the way to 0 to 24. All right, so let's mark our calibrations. We're starting from 0, so this is 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, we can see that our intervals are varying from 5 to 4 to 3, like that. They're not even. Okay, so let's enumerate our calibrations here. So we're going to have, this is x1, x2, x3, x4, x5, x6, and x7. Okay, so for your left rectangular approximation, you're going to pick all the points to the left of the right endpoint. So we're going to neglect x7 here. All right, so let's go ahead and find out what our widths are. So for W1, this right here is W1. W1 is equal to 5. You can close this 5. W2 is equal to 4. W3 is 4. W4 is 5. See how the subintervals are irregular. W5 is 3, and then the last with W6 is 3 also. Okay? Alright, so let me write down the formula that we're going to be using here. LRAM using 6 of intervals is going to be, let's see, W1 times f of x1 plus W2 times f of x2 plus W3 times f of x3 plus W4 times f of x4 plus W5 times f of x5 plus W6 times f of x6. Okay, so this is how it looks with the left-hand rectangular approximation. If we're doing right-hand rectangular approximation, we just start with x2, 3, 4, 5, 6, 7. Okay, so that's the difference. Now let's plug in our values in here and compute the approximate distance covered. All right, so W1 is 5 times f of 0 plus W2 is 4 times f of 5 plus W3 4 times f of 9 plus W4 5 times f of x4, which is 13, plus W5, which is 3 times f of 18, plus W6, which is 3 times f of 21. All right, so to find these output values, all we just simply do is make use of this chart right here to find out f0, 5, 9, 13. We all know that. Anyway, so let's go ahead and do that. We're going to have 5 times 0 plus 4 times 30 plus 4 times 50 plus 5 times 68 plus 3 times 82 plus the last one 3 times f of 21, which is 90. Alright, if you put all this together and calculate it, you're going to come out with 1,176. What's the unit of our distance here? Meters. Okay, so this is the total distance the particle covered. Alright, let's take a look at question number 2. So for number 2, we're going to evaluate a definite integral. Evaluate the definite integral from -5 to 5 of the function 6 minus the square root of 25 minus x squared dx. Okay? Now this is a situation where we can make use of the geometry of the appearance of this function on this interval to compute what the area is. Okay, because we know the definite integral is basically the area between the curve and the x-axis. So what kind of function is this? What does it look like, a graph of this function? So you notice you have r squared minus x squared. This is automatically a semicircle with radius 5, but we have some translations and reflections happening here. So this minus means it's going to be looking at the bottom hemisphere, the bottom semicircle, sorry, and then 6 units involves a shift. Okay. Alright, so before I graph it, let me write it in word form. So this portion right here, the integrand is a bottom semicircle shifted 6 units up. Okay, so that's basically the situation we're dealing with here. All right, let me give you a sketch of the situation, and then we can use that appearance to determine the area. All right, so there goes our coordinate system. Like that. All right, so there you have the semicircle, and it goes from -5 all the way to 5, centered at the origin, but we're to shift it 6 units up. Okay, so it's going to go 1, 2, 3, 4, 5, 6. We're going to shift this entire semicircle 6 units up. So let's go ahead and do that. Shift it up like this. Okay, so what we're looking for now, this is the resulting function, is the area underneath this curve. So between this function right here and the x-axis, that's the area that we're looking for. That is the value of this definite integral. All right? Okay, so you can clearly see that this is an easy geometry problem. We can visualize this as the difference between the area of a rectangle and the area of a semicircle. Right? So this is what we're looking for here, this area down here. So simply the entire thing is a rectangle, and then you subtract the semicircle from there. Okay, so let's go ahead and do that. So let's write it in word form. Area equals area of rectangle minus area of semicircle. Okay, so what is the area of the rectangle here? The entire length is 10 units, and it's 10 units wide, and you go up, and the length is 6 units. 1, 2, 3, 4, 5, 6. So the area of the rectangle is 6 times 10. Minus the area of the semicircle, the radius is clearly 5, so pi r squared divided by 2, so 1/2 pi r squared, 5 squared. Okay, do the calculations, you end up with 60 minus 25 pi over 2. All right, so this is the expression of the definite integral. Okay, so this is equal to, let's write on the left side of the expression what we're asked to find. The definite integral from -5 to 5 of 6 minus the square root of 25 minus x squared. Okay? Alright, so that's that. Alright, let's take a look at question number 3. This is another definite integral problem, so we have to evaluate the definite integral from pi over 3 to 5 pi over 6 of cosecant x cotangent x dx. Okay, so this is a problem where we can use the antiderivative to find the integral here. Okay, so if you think about the antiderivative, what do you differentiate to get cosecant x cotangent x? Remember from your differentiation rules that the derivative d dx of cosecant x is equal to cosecant x cotangent x, negative cosecant x cotangent x, right? So this is a derivative. In order to compensate for this negativity, we know that the derivative d dx of negative cosecant x is simply going to be the opposite of that, which is cosecant x cotangent x. Okay, so using the derivative, here we can determine what the antiderivative is here. So if we evaluate the antiderivative of cosecant x cotangent x, that's going to become negative cosecant x, right, evaluated from pi over 3 all the way to 5 pi over 6. Alright, so what we're using now is FTC part 2. Basically, you find the antiderivative and you evaluate it at the upper limit minus the antiderivative at the lower limit. So this is going to become, and another thing we can do is factor out this minus so we don't keep using it over and over again. Let's put the minus on the outside. So negative parenthesis cosecant 5 pi over 6 minus cosecant pi over 3. All right, now so I'm going to evaluate these two. Cosecant 5 pi over 3 is 2 minus cosecant pi over 3 is 2 root 3 over 3. If you distribute the 2, I'm sorry, the negative to both quantities, you're going to have 2 root 3 over 3 minus 2. You can find the LCD, put this over 1, and then multiply this by 3 top and bottom. By 3, and then your final answer is going to be 2 root 3 minus 6 divided by 3. All right, so that's that. All right, let's shift our attention to question number 4. Question 4, we're to find dy dx. If y is equal to the integral from 4x squared to 5 of the square root of 1 plus 5 sine squared t dt. Okay, so this is a FTC part 1 that we're going to be using here. In this case, you notice that we have a constant limit as the upper limit of integration, and we have a variable limit as a lower limit of integration. Okay, so remember the procedure for this. So y prime or dy dx is going to be, we're going to use a shortcut here. You're going to, we're going to substitute the upper limit into this function, which will be the square root of 1 plus 5 sine square 5. But when you multiply it by the derivative of this using the chain rule, you end up with 0. Okay? So evaluating the antiderivative of this, the derivative of the antiderivative of this function at 5, you get 0. Minus, if you evaluate this, the derivative of the antiderivative of this at 4x squared, all you have to do is simply plug in 4x squared into this function, which would be the square root of 1 plus 5 sine square. Instead of t, you're going to put in the 4x squared right there, and then multiply this by the derivative of 4x squared. So the derivative of 4x squared is 8x. Okay? So if you simplify this a little bit more, your final answer will be negative 8x times the square root of 1 plus 5 sine square 4x squared. This is an application of FTC part 1. All right, let's take a look at question number 5. So for question 5, we have to find the average value of a function. So find the average value of f of x equals negative 4 over 1 plus x squared on the interval negative root 3 all the way to 1. Okay, now the formula for an average value of f on an interval AB is given by the reciprocal of the length of the interval b minus a times the definite integral of the function from a to b, like that. Okay, all right, we can see in this problem that our a is the lower boundary of our interval, negative root 3, and b is the upper boundary of our interval, which is positive 1. Alright, so let's plug in a, b, and the function into our formula here. So the average value of our function is going to be 1 over b, 1 minus a, which is negative root 3, okay, times the definite integral from negative root 3 to 1 of the function negative 4 over 1 plus x squared dx. Okay? Alright, now thinking back to your differentiation rules, does this look familiar to you? To help juggle your memory, I'm going to factor out this negative 4 here from the integrand, so it becomes negative 4 over 1 plus root 3 times the definite integral from negative root 3 to 1 of 1 over 1 plus x squared dx. Do you remember the function that results in this function upon differentiation? Do you remember the derivative of your tan function? What's d dx of tan? Inverse tan, sorry. The derivative of inverse tan is 1 over 1 plus x squared, right? Alright, so we're going to apply that here. So this is going to become, let's change our color. This is going to become negative 4 over 1 plus root 3 times the inverse tan of x evaluated from negative root 3 all the way to 1. Okay, we're using FTC part 2 here. Evaluate the antiderivative of this function at this limits, the difference of those limits. So you're going to have negative 4 over 1 plus root 3 equals, times the inverse tan of the upper limit first minus the inverse tan of the lower limit. Okay, so that's what you're going to compute. Okay, so using your knowledge of trig, we can figure that this is negative 4 over 1 plus root 3 times inverse tan of 1 is pi over 4, and inverse tan of negative root 3 is negative pi over 3 there. And then and find the LCD and simplify. Let's go ahead and do that real quick. So we have negative 4 over 1 plus root 3 times pi over 4 plus pi over 3. Okay, so if you find the LCD, you times this by 3 top and bottom. 3, and you times this by 4 top and bottom. And you combine it, you have negative 4 over 1 plus root 3 times 7 pi over 12. Okay? So let's simplify this a little bit further. 4 goes here 1, 4 goes here 3 times, and you're going to have negative 7 pi divided by 1 plus root 3. So let's simplify the denominator here, since we can have a radical in the denominator. So we're going to multiply by the conjugate of this radical right here. So 1 minus root 3 top and bottom. And the numerator will simply have negative 7 pi times 1 minus root 3. And then in the denominator, this is a difference of squares in factored form. So if we multiply together, we just have 1 square minus root 3 square. there. So that's going to yield, oh yeah, we had a 3. Let's not forget that. There's a 3 down here. So I have a 3. And then we still have to retain that 3. Okay, so let's see. In the numerator, I have negative 7 pi times 1 minus root 3. And then in the denominator, we'll simplify it. Let's see what we get. We'll have 1 minus root 3 squared is just 3, right? So 1 minus 3 is going to give us positive 2. Negative 2 times 6 is going to give us negative 2 times 3 is going to give us negative 6. All right. So our final answer is simply going to be 7 pi times 1 minus root 3 over 6. Okay, because this minus is... Good day, students. Welcome to part 2 of the definite integral review. Let's go ahead and take a look at question number 1. For number 1, we are to evaluate the following expression. Evaluate the definite integral from 0 to 3 of the derivative d dx of x e to the 3x dx. Okay? Alright, so let's go ahead and evaluate this. So if we think about it, if you're evaluating a definite integral, what do you do first? First thing you do is you take the antiderivative of the integrand, and then you evaluate it at the limits of integration. Okay, so another way I can write this expression right here is basically find the definite integral, find the indefinite integral of this expression, the derivative d dx of x e to the 3x dx. Okay, now after finding the indefinite integral, whatever the result is, I'll evaluate it from 0 all the way to 3, right? So evaluate it from 0 to 3. But if you look at this situation right here, what is the relationship between the integral and the derivative? They are inverse operations. Okay, so when you're looking for the indefinite integral of the integrand, which starts with a derivative, these two operations basically neutralize each other. They cancel each other out. So what you're going to be doing in actuality is evaluating this expression right here, x e to the 3x from 0 to 3 using FTC part 2. Okay, so what does this mean we should do? We evaluate this expression at the upper limit minus this expression evaluated at the lower limit. So we're going to have 3e to the 3x, e to the 3 times 3. Plug in 3 into the 2 x's. 3 times 3 minus 0 times e to the 3 times 0. You can clearly see that this entire expression is 0, and you're left with 3 e to the 9th power. Alright, so there goes your final result. Alright, let's take a look at question number 2. It says, given the graph of the acceleration of a particle below, so this function right here, f of x, is the acceleration of a particle, and the velocity is given by v of t equals the integral from 1 to t of f of x dx. Find the following. Alright, so let's start with the a part. So with the a part, we have to find two things, v of negative 2 and v of 3. So let's start with v of negative 2. So v of negative 2 just involves substituting negative 2 for t here. So how does that affect this expression? It makes it the integral from 1, instead of all the way to t, is going to go to negative 2 of f of x dx. All right. So we know what the integral, the definite integral is, right? Is the area underneath the curve, between the curve and the x-axis. So if we look at this order of integration, you'll notice that it's actually going in reverse order. You're going from 1 to -2. So can we switch the order of integration here? The answer is absolutely, we can. So let's go ahead and do that. We can write this as negative of the integral from -2 to 1 of f of x dx. So we're looking at the area underneath the curve from -2 all the way to +1. All right. All right, so let's go ahead and evaluate this. So if we do that, we're going to have a composite shape. We have a triangle here, and we have a square. Okay. So if we do the area of this triangle from -2 to 0, that's going to be 1/2 of the base. The base is 2 units long. 1/2 of the base times the height. Since it's going upside down, we're going to have a -1 unit as a height. Okay? And then plus the area of the square. The width is 1. And the height, since it's going down, is -1. So we don't want to forget this minus that we factored out. So let's put the minus in front here. Alright, so remember this is the area of the triangle. This triangle right here. Plus the area of the square. This square right here. So that's going to yield negative. This entire expression, these two 2's cancel out. -1. 1 times -1 is -1 minus 1. Alright, so you have negative times -2. And your final answer is 2. Alright, so for the second part of part A, we have to find v of 3. So let's just call that double I. V of 3 is similar to this. We're going to look for the integral from 1 to 3 of f of x dx. Okay? So in this case, now we're going from 1. We want to look for this area all the way to here, this area right here. Okay? So what can you guess what the answer is just by inspection? These two areas are identical in size, but this is negative and this is positive. So what happens when you add two identical opposite quantities? They cancel each other out to 0. So this should be 0. Okay? Alright, let me show you the mechanics to prove that that is actually the case. So let's use geometry here. So the area underneath this curve is 1/2 base times height. Let's go ahead and compute that. We're going to have 1/2 times the base, which is 1 unit long, times the height. Now, since the height is going downstairs, underneath the x-axis or it's upside down, is going to be negative. All right, plus the area of this triangle on this from 2 to 3 is 1/2 base of 1, height of +1. Okay, and you can clearly see we have -1/2 plus 1/2, which equals to 0. All right, let's move on to part B. Part B, we have to find the maximum velocity for this particle and where it occurs. Now, f of x is equal to the acceleration. And we know we have the continuum, position, velocity, acceleration, and jerk. So the acceleration is the derivative of the velocity. So this graph right here is equal to v prime of x. Okay? So this is v prime of x. To find the max, we want to look for where the function changes from increasing to decreasing. Okay? That's where you have your maximum located at. Remember, the sign of f prime tells you the direction of f. Okay? So let's do a number line. If you want to find what we're looking for here is the extrema. That's what we're looking for. So using this graph of the derivative of velocity, let's see, we're going to connect the sign of v prime, which is a, with the behavior of f. Okay, so we see a sign change here, -2. We see a sign change here, +2. Okay, so remember what we're looking at is a sign of v prime. Okay, and that tells us the behavior of v. Okay, and v prime is also the same thing as a. So from -3 to -2, so v prime is negative, which means, I'm sorry, it's positive because it's above. This is positive and this is negative. So this is positive, so that means that v, the velocity, is increasing. From -2 all the way to 2, it's underneath the x-axis, which means that the v prime is negative, indicates the function is decreasing. And then from 2 all the way to 5, v prime is positive, which indicates that the function is increasing again. So if you go from increasing to decreasing, what is this extrema? What can you classify this extrema as? If you're increasing and you start to decrease, this right here is a maximum, a relative maximum on the domain. And on this extrema right here, if you're decreasing and then you start to increase, this is a what? This is a minimum. Okay? So this clearly shows us, since you're going from positive to negative, that you have a maximum. That's the only maximum we have at t equals -2. Alright, let's take a look at question letter C. It says, when is the jerk of the function less than or equal to 0? Okay, when is the jerk of the function less than or equal to 0? So, how do you get jerk from acceleration? You know that a prime is equal to jerk, the derivative of acceleration. So if this is the acceleration curve, what is the derivative of the acceleration? That's the question. The derivative of the acceleration graphically is the slope of the tangent line at every point. So since these are all straight lines, the slope of the line can basically tell us what the slope of the tangent line is, since they're basically the same line. Okay? Alright, so we're looking for where the jerk is less than or equal to 0. So basically we're looking for where the slope of the line, slopes of A, is either equal to 0 or negative. Okay? So let's look at this line. Where do we have negative slopes? So from here you can see that the acceleration is decreasing from -3 all the way to -2. So guess what? A prime is negative on this interval right here. The slope is always negative. Here, the slope is going to be what? Here the slope, A prime, is equal to 0, since you have a horizontal line. Okay? And then here it's positive, we don't care about that. And then from 3 to 4, A prime is equal to 0 again. And then from 4 to 5, A prime is negative. Alright, so when we're looking for where it's negative or equal to 0, our answer is going to be as follows. It's going to be in the intervals from -3 to -2 and then to 0, because -3 to -2 to 0 for negative, and then all the way to 1 for 0. They're both included. So from -3 to 1, and then from 3 to 5, because it's 0 and then negative from 3 to 5. So this is where your jerk is less than or equal to 0. Okay, so don't forget that A prime of t, the derivative of acceleration, is your jerk. Okay? Alright, let's take a look at option letter D. Where to find the intervals where the velocity is decreasing. So v of t is decreasing when v prime, which is equal to a of t, is what? Negative. Okay? So we have to go back to the graph and look for where the acceleration is negative. Anywhere the acceleration is negative, that means that its derivative, which is velocity, is going to be decreasing. Okay? So you notice we already talked about it here. From -2 all the way to 2 is decreasing because the acceleration is underneath the x-axis. Remember, this is your acceleration curve. Okay? So v is decreasing from from -2 all the way to 2 because its derivative, because v prime of t is negative on that domain. So that's that. All right, let's take a look at question number 11. I'm sorry, question number, where are we at? Question number 3. So for question 3, we're going to be using the rules of integration. So we have to find k so that the integral from 2 to t of 2 root x dx plus k is equal to the integral from 5 to t times 2 root x dx. Okay? So in order to do this, we have to look for a way to isolate k and combine these two integrals into one if possible. Notice they have a similar limit of integration. So if they have a similar limit of integration, then it's possible for us to combine them. All right? So what I'm going to do is I'm going to move this integral to the left. So we have k equals the integral from 5 to t times 2 root x dx. So you got to subtract this integral from both sides. So it becomes minus the integral from 2 to t times 2 root x dx. Now in order for us to stitch these two integrals together, we have to make sure that the upper limit of one corresponds to the lower limit of the other. Alright, we can clearly see that that's not the case here. So on this integral, we can switch this around using the order of integration rule. So this becomes the integral from 5 to t of 2 root x dx. Try that properly. 2 root x dx. Fix that. And then we're going to switch the order of the other one. 2 root x dx plus the integral from t to 2 of 2 root x dx. Alright, so this now becomes the integral. We can now combine them together from 5 all the way to 2 of 2 root x dx. That's what k is equal to. And then if we want to put it in ascending order, we can use the order rule of integration again to write this as the integral, the negative of the integral from 2 to 5 of 2 root x dx. Okay? So you remember that if you switch the order, then you have to introduce a negative. So let's go ahead and evaluate this integral using the integration rules. So we're going to have, let's express this as factor out -2 from 2 to 5 of x to the 1/2 dx. Now what's the antiderivative of x to the 1/2? It's simply going to be x to the 1/2 plus 1 over 1/2 plus 1. Okay? So this is going to be -2x to the 3/2 over 3/2. And then if you simplify this, you have -4/3. That's if you reciprocate 3/2 and multiply by the top, you get that. X to the 3/2. Okay? So remember, we're evaluating this from 2 to 5 to get up the value of k. So k is going to be equal to, you're going to plug in the upper limit, -4 times 5 to the 3/2/3, and then you plug in the lower limit minus, well, let me make our lives easier here. So to avoid too many complications, I can factor out this -4/3. Okay, let's go ahead and do that. So put the -4/3 out here. I don't want to keep writing it over and over again. And then we're going to evaluate x to the 3/2 from 5 all the way to 2. Okay, so this is going to become -4/3 times 5 raised to the 3/2 power minus 2 raised to the 3/2 power, like that. So we can write this as -4/3 times, we can break this apart. This is 5 times 5 to the 1/2, right? 5 to the 1 times 5 to the 1/2 minus 2 to the 1 times 2 to the 1/2. Remember, when you multiply exponents, you add the powers, right? So when you split them, you can subtract the powers, express them separately like this, okay? So finally, we can write this as -4/3 times 5√5 minus 2√2. Okay? So there goes your final result. All right, let's take a look at the last question, question number 12. I'm sorry, question number 4. So for problem 4, we're to find f4 if the integral from 1 to x of f of t dt is equal to x to the sine x. Okay, so we're going to go ahead and look for this. So to find this, to find f of 4, first thing we have to do is find f prime of 4, okay? I mean f prime of x, and then evaluate it at 4. So f prime of x is equal to, is basically the derivative of the integral from 1 to x of f of t dt, which is equal to the derivative of this expression x to the sine x. Okay? Now if you have a situation like this, a function raised to a functional power, we're going to have to use logarithmic differentiation. Okay? So let's say y is equal to this function right here, x to the sine x. Okay, we want to use a variable that we can solve explicitly for. So now if we differentiate both sides, that will be basically be what dx of this expression is. But before we do that, we need to power down this exponential function. So what we'll do is we'll take the natural logarithm of both sides. So ln y is equal to the natural logarithm of x to the sine x. Now using the properties of logarithms, I can power this exponent down. So this can be written as the natural logarithm of y equals sine x times the natural logarithm of x. Okay? Now we're going to differentiate this side, both sides of the equation. Alright? So if we want to differentiate both sides, let's rewrite it again. So ln y prime equals sine x ln x prime. So on the left side, using implicit differentiation, we're going to have the derivative of ln y is 1 over y times y prime. And on the left side, we're going to use the product rule. So this is u, and this is v. So we're going to have vu prime ln x, derivative of sine x is cosine x, plus, so this is vu prime plus u v prime, so u is sine x, and the derivative of ln x is 1 over x, so sine x over x, like that. Okay, so if we want to get y by itself, y prime by itself, y prime is equal to y times ln x cosine x plus sine x over x. But we know what y is, right? Earlier we said that y is equal to x to the sine x. So that implies that y prime is equal to x to the sine x times ln x cosine x plus sine x over x. Okay, so this is what f of 4 is. Okay, so this is what f of 4 is. So what we're going to look for now is this is f of x. Okay, this is f of x right here. So I made an error in my notation. This is supposed to be find f of x. Okay, f of x, since this is the integral of f of x, so f of x would be the derivative of this entire expression. So this is right. This is f of x. Sorry about that. All right, so if this is f of x, what is f of 4 going to be? F of 4 is simply going to be what you get when you evaluate this function at x equals 4. So you're going to have 4 raised to the sine of 4 times the natural logarithm of 4 cosine 4 plus sine 4 over 4. Alright, so there goes your final result. Thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel. And please post a comment to let me know what you think about this clip. More clips can be found on math.serve.com. Thanks again for watching, and have a wonderful day.